I would like to welcome Dr. Sri Vallabha Devi, Director, Data Science at Tiger Analytics and adjacent faculty in the Department of DS and AI at IIT Madras. Professor is with us to deliver the talk on GenAI models for medical IoT data analytics. I welcome you, sir. As part of his role at Tiger Analytics, he leads the team focusing on the problems in the various industrial domains like retail, transformation, transportation, manufacturing, and electric designs. In the past projects, he worked on developing deep learning models for video analytics, machine learning models for anomaly detection and price predictions. Also, recommendation systems for retail clients and natural language processing models for information processing. His current projects are focused on reinforcement learning, generative AI, and optimization for various industries. As an adjacent faculty at IIT Madras, he teaches applied AI/ML topics and guides masters and dual degree students in their final year projects. Prior to this, he also worked as a postdoc fellow at IIT Madras in statistic analysis of liquor sprays. His doctoral thesis was on large eddy simulations of praise, a branch of computational fluid dynamics. His areas of expertise are machine learning, statistic analysis, uh, reduced order modeling, simulations of physical systems, and scientific computing. He holds BTech degree in mechanical engineering from IIT Madras also, and a PhD in aerospace engineering from IISc Bangalore. I welcome sir once again for your wonderful talk. The session is yours, sir.
Yeah, thank you very much, Dr. Praveen, and thank you, NIT Puducherry, for the opportunity. So, good evening, participants, and today maybe we will talk about generative AI for medical IoT data analytics. I know that as a part of the FDP, you have already heard lectures about medical IoT and smart healthcare system security. So, something about data security you might have already heard. And then you also heard about medical IoT device architecture and communication. How do we set up IoT systems? So these are the two that might have been covered yesterday, right? So today we will look at once the data comes into this system, or once we are able to set up systems and capture IoT data, what can we do with the data would be the focus of today's talk. And I hope all of you can see my screen. So this will be the agenda. So because this is the first talk on machine learning or generative AI in this FDP, I will try to cover something on machine learning, deep learning very quickly before we go to generative AI and what we can do with the generative AI for medical IoT data. So this is the brief outline of the talk, and any questions anywhere in between, please feel free to comment, and then I can try to answer those questions. Yeah, so basically, if you look at the evolution of the civilization, right, this is a very generic slide that will cover, that will try to put something in perspective for us. So nearly 2,000-3,000 years ago, people were working on transforming material. Stone tools, bronze tools, iron tools. That was what people were doing, say, 2,000 years ago. And roughly 200 years ago, in the 1800s and all, people were trying to transform energy. People from water power or from using water in the running streams to steam engine, electric power, combustion power. All this was going on nearly 200 years ago. And in the last 40 years or so, from 1980s or 1970s, this became the era of information transformation. And some of you might remember, some of you, if you are slightly like in the 35s and 40s, you might have heard about information and communication technology, ICT, as a probable topic in your earlier studies or some focus areas. So 10-15 years ago, if you say what are the research areas, ICT would have been a good research area, information and communication technology. That was about how do we capture information, how do we store information, and how do we transmit information. So essentially, it is like capturing various details about something and being able to present their details to other people who are in need of the information. A simple example is a railway reservation system. If you want to book a train ticket, say from wherever you are to say Chennai, then the point would be the railways website today will be able to tell you how many tickets are available in each class, say sleeper class, second AC, first AC, and so on. So that visibility is what is ICT. Now, moving from there, right now we are in the era where we are using that information to derive insights and to be able to act upon the insights. For example, today, again going back to the train tickets, right? There will be apps and there will be services which will tell you which train ticket is most likely to get confirmed. know that without the reality happening. That is enabled by models. There will be some or the other prediction model which will say on this train for this waiting list, the probability of confirmation is say 80% or 90% or 95%. So using that understanding, they're able to today tell you that, okay, if you want a confirmed ticket, go to this train or go to that train. So the example here is for just to tell you the fact that after we capture relevant information, today we are able to build models on the information to make predictions which are reasonably correct. So how did AI or artificial intelligence come into play? This came into play with the rise of ICT, the information communication technology that I told you a moment ago, right? So industries that had large human interactions. So banks will have large interactions with customers, retail stores, lot of people stores and make their purchases. And then advertising, right, with the availability of email and messages. Paper posters on the wall, I can send you a video clip of a movie, or I can send you an advertisement about a particular product via WhatsApp or whatever. So with various tools becoming available, marketers or advertising professionals started reaching out people directly. Now the point is, when we are able to reach out people directly through digital means, we can also record the people's response or behavior to what we are sending them. For example, if you think of a movie poster, no, if there is a poster on the wall, 100 people might see the poster, but 10 may dislike the poster, 9 and 20, 30 may have no opinion, and the rest of the 60 might like the poster. But there is no way for the advertising guy to know how many people like the poster. But today, when they send you the same ad in your Facebook app or say Instagram app, from your swiping information, you keep swiping without stopping, then it is disinterest. You pause and see what is going on, that is interest. So with that kind of information, right, companies are able to understand what kind of advertising message would you like. Should I put the message very clearly? Should I put the message in a fancy way? That kind of stuff people are able to understand. So when these industries are collecting information at scale, meaning I'm able to reach out to everybody, observe their behavior and then record their behavior. Once that was accomplished with ICT, AI or artificial intelligence became the tool to predict human behavior using this data. So how did it predict, or how does it enable us to predict? For example, if you think of a bank, and today people log into the bank online and do various things and search for various things, right? So from your activity, the bank may know whether you are looking for a loan or whether you are interested in making a fixed deposit, because based on the website pages that you see, based on what you do in the banking page, they'll be able to understand. Similarly, in the advertising world, right, based on what you are searching or what kind of messages you engage with, companies are able to tell, okay, for this person, I should send a message like this and not in a different way. So that is how AI is enabling the prediction of human behavior and enabling companies to do more. Now, this is for the generic world. This is for the common or the regular world where a lot of other things happen. But that also led to expansion or what we call adoption of AI elsewhere. Because the AI algorithms became so popular and they became so useful, other fields started to think of, okay, can we also add in AI and make some progress or get some advantages? So the advances in AI led to wider adoption in the field of medicine. Like all fields, medical field also started adopting artificial intelligence after it took off in other fields like retail, banking, and so on. So one of the earliest one is about the drug discovery, where AI was able to find out the better ways to, or structure of proteins. This is a problem from 2018 or so, or even before that, almost like 10 years ago or so, where Google had a model that was able to find out protein structure. And this protein structure prediction is a very common problem in drug discovery. When people are trying to develop medicines, these medicines or the medicine in the drug must actually go and stick to the human tissue to be absorbed by the human body. So which protein will get it, will get better binding was a problem that a medical field was searching for a long time. And the protein structure is an important aspect of that. And earlier, the protein structure was predicted by trial and error methods. People had simpler tools with which they try to get an approximation. But Google came up with a better tool called DeepFold, which was able to give protein structure prediction. And that accelerated drug discovery by a significant amount, because the initial testing of the 5,000 to 10,000 compounds and then the preclinical trial of the 250 compounds, right? This became accelerated because they knew which drug will be the best one to, or which protein will get better absorption by the human tissues. Another problem was about treatment selection, and this problem is more prominent in the Western world, where healthcare is universal, meaning everybody has to go to the same hospital and wait for treatment there. So you're in US and Europe, where people have to wait for treatment, AI and ML models are used to prioritize people for treatment. There were multiple people of multiple age groups waiting for a surgery, for a specific kind of surgery. Let us say there is a cardiac surgery that needs to be done, or maybe some surgery of some other part of the body, and the doctors were few. Let us say there were limited doctors and there are more patients waiting. So there is naturally a queue or a waiting system. So within that queue, whom to prioritize and whom to make them wait, was a prediction that was always challenging for the medical practitioners. And people had kind of adopted AI models to prioritize treatments. For example, right, there may be a small child for whom the surgery is critical, and there may be an old person also waiting for surgery, and there may be somebody in their 20s, 30s also waiting for surgery. Depending upon who will require the immediate treatment, the doctors can prioritize, and AI models made some advances in prioritizing patients in the healthcare services. And one other example that is well known by now is the diabetic retinopathy prediction from Google. Again, Google had a deep learning solution. We will see what deep learning is as we go on, right? We will see what deep learning is. So Google had a deep learning solution to predict whether a person is suffering from what is called as diabetic retinopathy. Retinopathy is a condition of the eye where the retina detaches from the eyeball and the person stops the vision. The person loses the vision, and it is caused by diabetes. So because this is a disease that affects many people, but there are not many specialists, it was very difficult to get the diagnosis correct. So Google built a deep learning model that would take images of the retina, which is called fundus photography, and from the images of the retina, it was able to predict whether a particular eye is suffering from diabetic retinopathy or not. And this deep learning model was able to match and do better than the expert doctors in many scenarios, and it was a good success and had a wider adoption. So these are three examples of how AI or artificial intelligence or machine learning were adopted to the field of medicine. So this is again some few years ago, not like yesterday. These are all like a few years or like almost 7 or 8 years ago, and so on. Now with the what do you call proliferation of digital devices, right? Semiconductors and chips became widely available, because of which we were able to build various IoT healthcare devices, meaning these are chips that can communicate their data and their status to the internet, but these are devices which are related to medical treatment. And there are a wide variety of these devices. Just for an example, for us to be clear about the spectrum of devices that we are talking, there are wearable devices like smartwatch. Today, all of us know Apple Watch or Samsung Watch. It is able to monitor heart rate, blood pressure, lot of things. So there are wearable devices. There are implantable devices. These are devices which are specialized and are implanted into the human body by doctors. We cannot simply buy and keep. So these are like pacemakers or biochips or glucose monitoring implants and all. So these are some implantable devices. Then there are more complex devices at hospital. So when people join hospital for say tertiary treatment or secondary treatment, there are various devices in the hospital which are connected to the internet. Bed sensors, IV pumps, and inhalers are some examples. Then there is another group of devices which are at-home medical devices. These are not portable per se, but then you can still have it, or these are things that you use at home, like thermometers and home monitoring kits. Then there are remote monitoring systems about hospital equipment and hospital operations, environmental monitoring about air quality, and then there are emergency response systems, like when people have falls, old people have a slip and fall and all those kinds of things, right? So there can be alerts to emergency response systems. So these are various spectrum of IoT healthcare devices, and we will look at what AI can do in each of these areas. So AI has varied use cases in the data that is collected by these devices. So what can AI or generative AI do in all these areas? That is what we will see as we go forward. Okay, now coming back to the original AI ML kind of theory, right? So artificial intelligence is about sensing, reasoning, and acting or adaptation. This can be based on rules or a learned function. So what do we mean by this? Any system that is intelligent enough can be called AI. Now, what is an intelligent system? Let us say your college has smart lights that will turn off when people leave the room. So that is a classroom with lighting, but if there are no people in the room, the sensors will detect that the room is empty and then will turn off the lights. That system can itself be called as an AI because it is acting based on a set of rules. If there are people, keep the lights on. If there are no people, turn off the lights. Then machine learning is a branch of or a subset of artificial intelligence where we typically do not depend upon rules here, but ML is based on a learned function. So we build models on structured data, which is tabular data, and then with that we will try to understand or make decisions. So we will see each of these in some detail as we keep going forward. Then deep learning is another branch of or a subset of machine learning itself. So deep learning uses neural network based models, and these models deal predominantly with unstructured data like images, video, text, and speech. And deep learning has wider applications compared to machine learning because it can deal with a wide variety of inputs. It can deal with videos, images, speech, text, written documents, and so on. Then generative AI finally is a subset of deep learning. It will use neural networks extensively, and it has much more advanced capabilities than what you would get in the deep learning alone. So we will see. We will try to understand what each of these is in some detail, see some applications, and then progress to the generative AI piece of it. Okay. So now, any questions or any thoughts? Maybe I'll just pause for a moment to see. Okay, looks like there are no questions. Then maybe I'll move on. So basically, right, we'll come back to what is analytics. So analytics or data analytics or machine learning or AI, whatever, right, is about organizing the information or the data that you capture. You capture a lot of pieces of information which you can call as data. We try to process them to get to some insights. And once we process them, understand the insights, we can then build models on them. Given the insights, right, we can try to predict some behavior, and that behavior prediction is called as modeling or building up knowledge. And then based on the models, we can then generalize and say that this is what I can state about the system or about the phenomena. So for example, right, you take data, you sort it, arrange it, and you can visually present it, and then eventually explain the data with a story. The same is conveyed by the other two infographics. So there is data, which when you structure by doing some processing becomes information, which when you do some structuring based on the beliefs that you understand, it becomes knowledge. And based on the knowledge and you process further, you will go to wisdom. Okay, so analytics is the process of analysis of raw data to draw insights, to gain knowledge, and to act upon that knowledge. That is what analytics is all about. So analytics, data analytics, machine learning, AI, ML, all these can be considered to be the same thing because the definition is not very rigid. The definition is gray, and a lot of things fall in many buckets. So if I say building a predictive model, is it deep learning or machine learning or AI or data science or data analytics? It would fall in all of them. Predictive models occur in all these groups. So the definition or the separations are gray, and all these are more or less you can think of them as the same. Okay. So when we come to analytics, right, there are four distinct what do you call classifications or groups of analytics. The first one is what we call as descriptive analytics. This is about telling what happened. So if something happened, no, what happened is the understanding. In the medical setting, right, you can think of it like a doctor talking to a patient to understand what happened. The patient might have told that I ate something, I ate an ice cream, and then I got wet in rain, and then after coming home, I did not take bath. I just dried my head and went to sleep, and the patient ended up with a fever. So the doctor will keep understanding. As a doctor keeps talking to various people, right, he will try to understand what is happening and then try to conclude. So when we say descriptive, it is about describing what happened. So let us say a doctor talks to a patient and the patient says all this. I had ice cream, got wet in rain while I was going on a two-wheeler at home, and then I dried my head and went to sleep, and today I have cough, cold, and everything. So diagnostic analytics is the ability to link up these things. So when we say descriptive, it is easy for us to describe what happened, but diagnostic analytics would require some practitioner, somebody who knows something about the field. So a doctor would most likely know, and similarly, right, elders at our home also will know. If you get wet in rain, they will say take bath with hot water so that you are not troubled by cold or other problems, right? So diagnostic analytics is to be able to understand why did something happen. So why did a person get fever? It might be because of getting wet in rain. Then the predictive will be something that will happen before, in the sense that even before the person catches fever, as soon as they come back home after getting wet in rain, being able to say that, okay, if you don't take bath now, you might catch fever tomorrow, is a predictive analytics part. These are all these areas are very much applicable elsewhere also. In the world of business, right? In the world of business, descriptive analytics would say, if you consider a supermarket chain, there is a chain of supermarkets where sales are happening, say like Reliance Retail or more or whatever you can think of in your state. Then suppose the sales at one supermarket started dipping. Descriptive analytics will say what happened to the sales. And you will say that, okay, the sales in this store are dropping, whereas the sales in the neighboring stores, nearby stores are all same. Diagnostic will be to understand why did this dip happen. So the dip is happening because Are there not enough people in the store? Is the store not open throughout the day? Or is the inventory not available at the store? All these kinds of things come in as questions in the diagnostic thing. So predictive analytics will be like if the inventory is not available at the store, the sales will drop, being able to say that. And eventually, the last one, which is prescriptive analytics, is about how can we make certain things happen. For example, if you go back to the rain and fever example, right? If somebody gets wet in rain, the prescription is go and take bath with hot water, dry your head thoroughly, and then cover yourself in warm clothes. That is the prescription to avoid fever. Similarly, in the business world, right, for the retail example that I gave you, the prescription can be to say, make sure that there are sales people in the store every day, make sure that there is enough inventory in the store every day, make sure that the store is opening on time every day. All these are the prescriptions. So all these are common to us. All of us would have seen this. Even in the context of, say, in your colleges, academic institutions, you will have your own set of prescriptions. Make sure you take attendance, make sure you have intermediate assessments for people, students, so that you do not end up with a surprise on the last day. These kinds of things are prescriptions, which would have come from various learnings throughout the way. Okay, so descriptive and diagnostic will deal with data. Whatever is already measured, we can do descriptive and diagnostic. But then, if you want to do some predictions, we need to do modeling. So what is it? We will see. So descriptive analytics is about presenting the data in various forms. So dashboards are simply charts. You can think of dashboard as a chart, pie chart, line chart, bar chart, whatever chart. So dashboards present the data statistics like mean, median, low, high, and all to see what is happening to the current situation. For example, right, in the ICU, there will be a monitoring tool which will monitor the BP, sugar, pulse rate, and all, right. So that is some example of a dashboard in a medical setting. And diagnostic analytics is about generating reports which will identify the connections between different sets of numbers. So if there are multiple observations, all these observations will indicate some condition. For example, again, going back to the medical world, if the BP is very high and the heart rate may be low, for example, it might indicate a specific condition for the patient, and the doctor will know what to do. So the doctor will say, okay, maybe I should take some, I should give some medication very urgently because this is a symptom of a specific problem. So descriptive and diagnostic will deal with data that is already observed. Whereas for predictions, what will happen later or what will happen to somebody else in a similar condition, for that we will need to do predictive analytics. And predictive analytics is about modeling to predict or forecast future numbers. And then the last step, prescriptive analytics. Now this is about building an approach to get the desired outcome based on the predictions. Meaning, predictive analytics will say, if I see this, I should do something to avoid a problem in the future. That is what predictive analytics will say. And the prescriptive analytics will say, what should I do to avoid such a problem in the future? That is what the prescriptive analytics will tell us. So models are required. When we say models, I am referring to what are called as machine learning models. So these are not medical equipment models. These are not anything else, but these are machine learning models. So machine learning models are required to predict unseen observations and future observations. What will happen to a different patient? What will happen tomorrow to this particular patient? So to do this, we will require what are called as machine learning models. Okay. So these machine learning models deal, and machine learning deals with models for data. When we measure some data, machine learning deals with the study of building models to predict on the data set. Okay. Then the mathematical models that learn from the data, and these mathematical models, essentially these models are all mathematical. There are functions of input data. They learn from the data and they make predictions on unknown and unseen data. This is what the ML models will do. Okay, and these models are used for predictive and prescriptive analytics. I've been talking about models. I will explain in a moment what these models are. But essentially, machine learning models means if I have some observations or some input features or something that I measure as an input, x1, y1, x, y, z, or three numbers that I measure for a given phenomena, then trying to predict an outcome based on this observed x, y, z is what the machine learning will do. Okay, so ML is essentially mathematical models that will learn to predict a particular value based on the input observations and which we can use for predictions tomorrow. So this is what machine learning modeling will do. So now we will come back to, or we will go to machine learning. Maybe if there are any questions, let me see. Okay, there don't seem to be any. Fine. So moving on, right? What is machine learning? We saw that modeling is required for predicting unseen or unknown observations. To predict them, we will require modeling. That is what we have seen. Now, what are the kinds of models? What models are useful? That is what we will see. So when we say machine learning is about building models on data. What data? That is the data that can be related to anything. If you look at hospitals, it can be patient data. If you look at retail stores, it can be sales data. If you look at banks, it can be the banking customer behavior data. What is the deposit? What is the withdrawal? How much money are people holding in the bank? All those are banking data. So machine learning will require data to learn. So what are the kinds of data that we are going to use or that is available in the world is what we are going to see now. So there are broadly two kinds of data. One is structured data and the other is another what is called as unstructured data. Unstructured data is what we are already familiar with. So this is data that is present in Excel sheets in the simplest form. No, structured data is anything that can be what we call stored in an Excel sheet. A simple example for us. Some of it can be like, for example, right? Some of the examples of structured data can be student attendance or student grades in your colleges, or it can be banking transaction information. There is a customer ID, there is a branch ID, and the customer deposited money or withdrew money or the customer took a loan, all that will be available in a table. And this data can be stored in tables. So when we store data in tables, for example, think of your student attendance. That attendance table will have a student name, student roll number, and then the semester or the year in which the student is in, and the subject that is of the current question, and then the attendance on every day. That will be the type of the table. So each column will have a specific type. One column can be student names, one column can be student roll numbers, another column can be a date, or another column can be a subject name. Then each row will be an observation. What is row? Row is like observation or entry about one student. So one student will have a roll number, name, semester, and then course, and then attendance across all the time. That's what this is. Okay. Now, the structured data can be stored in databases with keys and relations. So some of you or most of you might be familiar with databases like SQL and other things. So whenever there is a structured data, we can always store it in databases with keys and relations. All traditional software capture data in this form. By this we mean whenever we go to what do you call retail stores or banks and all, right, the data they capture is always structured data because it is tabular and numerical data. Okay. Then there is another group of data that we call as unstructured data. Unstructured data is more prevalent. Nearly 80% of the data in the world is actually unstructured, and that is where companies are now trying to mine or understand for insights. So that is where generative AI also comes into play. But what is unstructured data? Unstructured data is data that is present in documents, website comments, online posts, and so on. It can be also present in the customer care center recordings. People call customer care, raise their complaints. The recordings are a rich source of information. Then there can be images from cameras and videos from CCTV footages. For example, right, one common example of unstructured data would be, let us say there is a video, educational video or a movie or whatever it is, and there will be like hundreds or thousands of comments below the video. Understanding these comments will help us understand what is the viewer reception or the user reception of the video, whether the user says, thank you, it is very entertaining, or it is very insightful and all, or whether the user says it is a boring stuff. That is what you will see as unstructured data. And there, let us say 3 people write comments about an educational video. One person says the video is very good, the second person says boring video, and the third person says I did not learn much. We do not really know where exactly to search for what the person is saying. When I say we do not know where exactly, in the first comment, the video is good. The word good occurs in the end. And you can say that, okay, if you pick up the last word, you may say that, okay, the last word is an indicative of the customer or the user's understanding. The user may say, I like it in the end. But if you come back to the second, or if you come to the second comment, boring video, the second word or the last word is just video. There is nothing else in between. The boring word occurs in the front. So the challenge with unstructured data is which word to look at for what I want, which location to look at for what I want is not very clear. And that is where deep learning models come into play to deal with them and help us understand how do we gain insights from unstructured data. Okay. So structured data typically is tabular, stored in databases, Excel sheets, CSV files, whatever kind of databases that all of us are commonly familiar with, no? MS SQL or SQL or MySQL, a lot of databases are there, variants of the databases are there. Unstructured data is more prevalent. No, it is a policy documents or company policies or call center recordings, music, YouTube videos, lot of things are there. And there can be there is a rich source of comments on the internet, Facebook comments, LinkedIn comments, Twitter comments, Instagram, that this lot of things are there. Okay. So all these are examples of unstructured data. So machine learning will deal with structured data. When we say machine learning, we are talking about structured data that can reside in tables, which has a specific format. And in machine learning, there are three broad classifications of machine learning. These are supervised learning, unsupervised learning, and reinforcement learning. So what are they is what we will see. So supervised learning has two groups, regression and classification. We will see the examples and the definition of them as we go forward. Now, what is regression, what is classification? We will understand in some time. But essentially, supervised learning means I have labels that I'm trying to predict. Now, whatever I'm trying to predict for historical data, whatever I'm trying to predict is available as one of the observation. For example, if there is a person with so and so height and weight, what is the BP of the person? What is the normal blood pressure of the person given the height of the person, weight of the person, age of the person, and the body mass index BMI? Let us say there are 4 numbers: height, weight, age, and BMI are there, and there is a measurement of the heart rate. If these are there, and then we can build models on the data to predict tomorrow for a new person. If you say now there is a new person with so much, what do you call, this age, this BMI, this height, this weight, we will be able to predict the heart rate. Predicting heart rate is a numerical value, and regression is a model to deal with that. Classification is a second kind of supervised learning. We will see that again in a moment, but that will deal with yes or no decisions. Is a person at risk of diabetes or no? Is what classification will help us understand. Then the second category of models are what are called as unsupervised learning. And in unsupervised learning, there are no labels available. There are no labels in the sense I'm trying to predict something, but for historical data, I do not have any labels for what I'm trying to predict now. For what is of interest to me now, I do not have any historical records. That is where we will resort to clustering and anomaly detection. And reinforcement learning is another class where usually people are current day applications of reinforcement learning are like training robots and playing computer games. Today, if you look at humanoid robots to do things, they are trained with reinforcement learning. You try to open a lid, you try to do something, and by teaching the robot to do well or to penalizing the robot if it makes a mistake, reinforcement learning helps the robot to understand what is the best way to train. So that is what reinforcement learning will deal with. Okay. So the image on the right is an illustration where there are images of cats and dogs. The first column or the first set of images, there are labels. So these two are dogs and these two are cats. So there are labels associated with dog and cat. This is an example of supervised learning where I'm trying to predict the label, and this will be a classification problem. Given an image, tell me whether it is cat or dog is a classification problem. The second group of images, you see the same cats and dogs, but there are weights associated. The dog is 14 pounds. This dog is 18 pounds. This cat is 12 pounds, and this cat is 9 pounds. So in this example, right here, though there are images of cats and dogs, what is interesting is to predict the weight, and the weight is a number. It can be 18 pounds or 17.5 pounds. So this is a regression problem. Or we can try to train a regression model on this data to say, given an image or given a cat or a dog, I can try to predict the weight of the cat or the dog. And the last example is the one of unlabeled data where we just have images. We do not have any labels, any weights. And this is an example of unlabeled data where we can only do either clustering or anomaly detection. We cannot do any regression or classification on this data. So that is what the last image indicates. So wherever we get labeled data, we do supervised learning. And when we do not have access to labeled data or we cannot get labels, we resort to what are called as unsupervised approaches. Unsupervised approaches meaning there are no labels, there is nothing that I can do. Okay. Now, there are a set of other algorithms called A/B testing, time series forecasting, and recommender systems. And these algorithms are also used for various other problems or various problems. We will see some of these algorithms as it applies to the world of medicine as we go forward. Okay. Now, let me maybe just see if there are any questions. And okay, there are no questions, then I can continue. Fine. So what is regression? Regression fundamentally is the following problem, which is if I have given a set of values x1, y1, x2, y2, x3, y3, and so on, those are values given. I want to predict a continuous value y based on a value of x. So given an x value, I want to predict a y value. So simply think of it like this. Think of it like, I know a person's age. Can I predict the person's blood pressure in a sitting condition? Again, because there are other variabilities. Let us say that the person is well rested and sitting. What would be the blood pressure of the person when the person is sitting and rested for some time based on age? That can be a regression problem, simply put. And in such models, what we are trying to do is, we are trying to understand relations of the form y is equal to a plus bx. We want to build a simple relation where the y or the blood pressure is a function of the age and then some other constant value. And in engineering, no, for the people who are familiar with engineering, this is called curve fitting, except that this curve is a straight line. Most of us, when we do experiments, we will try to fit least square fit is what we try to do, and we try to get the coefficients. That is what is called as a straight linear regression. Okay. So we use least square fit to minimize the error, and this least square fit is what will give us the relation of the form y is equal to a plus bx, where we learn a and b values for a given data set. So suppose I give you a data set of age group and blood pressure, and you try to build a model. The model will give you an estimated blood pressure for a person of a specific age. Suppose there is a person of age, say 27 years, what would be the person's blood pressure? That is what you will be able to understand using a linear regression model. Now, how is linear regression applicable for healthcare? Okay, so when people apply for medical insurance policies in America and Europe, no, medical insurance is compulsory and kind of common. But because of the nature of the healthcare system, this can be costly. Sometimes, right, in India, we have at least the luxury of various private hospitals. We can go to some hospital that is useful for us. But in Europe and America, right, most of the time these are limited to few hospitals, and people try to, what do you call, go to the same hospitals, and the insurance pays. So insurance people are even more cautious because their hospital systems are kind of centralized or kind of restricted. So when people apply for medical insurance policies, the insurance company would like to know what is the likely cost of a medical treatment for this person. So there is a person of a specific age group with a lifestyle, with a particular income and educational background, and this person is taking an insurance for 1 year. If the person undergoes any medical problem, what is the likely cost of a medical treatment? This is the thing that the insurance company is interested in knowing. And how do they estimate that? From historical data, right? Same age group, people have applied to me last year, people have applied to me 1 year ago, 2 years ago, and so on. In the historical data, what has happened is the data that is available with the company. So say 3 years ago, 10 people like this applicant applied. And in the 10 people, 2 people went for treatment, and both of them had treatments worth, say, $5,000. So that is something that the company would know. So based on that historical data, they can build a linear regression model which will predict the healthcare cost of a person. Suppose there is a person who is applying for insurance policy with the age group, demographics, health conditions, and so on. If this person if you provide an insurance to this person, the likely cost of treatment would be so much. Is what a regression model will be able to provide to the insurance companies. And based on the likely cost, the company can decide either to give you the policy or to reject the policy or to quote a very high premium. So companies do that. If there is a high risk, the company will quote a high premium. If there is a low risk, the company will quote a lower premium. So regression model, one of the examples of regression problems is this, which is predicting healthcare costs. But a more direct example would be, if I observe a few things about a person, can I measure the unobservable features? Just like the BP and just like the heart rate and the age, right? If I am able to build a model to predict the heart rate or heartbeat rate as a function of the age, then given any person's age, no, I can simply estimate the heartbeat. It will be either 70 beats per minute or less than that or more than that. No, we can get a good estimate of the heartbeat. That's another example of a linear regression model. Then we'll go to classification. So classification is the second supervised learning problem where given a set of values, x1, c1, x2, c2, and so on. And if you observe, right, there are only two C's, c1 and c2 only are there, which are classes. It can either be a S class or a no class. So c1 can be S class, c2 can be no class, or vice versa, whatever way you want to think of. So given a set of observations, and then there are two classes, c1 and c2, we want to predict a class C based on X. That is what classification will do. And for classification, we try to build a relationship of the form y equal to logit of p, where log of p by 1 minus p equal to a plus bx. This is what we try to do when we do classification. There are Python codes which will do this automatically. We need not really write the codes, but there are Python programs that will do this automatically, but still. So we try to predict the class C based on a p-value. Now again, what is an example of a classification in the medical setting? Given a set of health parameters, whether the patient is likely to be diabetic or not is a very good example, because you may say the patient you might measure various things about the patient. Heartbeat, say blood pressure, heartbeat, something about the patient's fluids, urine and other things and all. And then what is the patient telling? Is he feeling weak? Are they feeling sleepy? Do they have weight loss? All this, if you see. With all this, we can try to build a predictive model to say what is the likelihood of this condition being diabetes. That is an example in the medical world, which is what most people do. So disease classification is an example. So for a person based on the observed symptoms, we can predict the probability of a certain medical condition. So this is what the doctors do regularly, right? Whenever we go to doctors and we say that I have this problem, that problem, then the doctor will immediately diagnose it to be something and then will start giving you medicines. So anybody goes to the doctor and says I have sore throat and I have fever, and based on the season, doctor will know whether it is viral or whether it is normal. And if it is viral, no, doctor will simply prescribe some specific medicines for you and tell that, okay, please go home, take rest, you will be all right. So how is the doctor able to diagnose it correctly? The diagnosis for this is coming from the historical data from similar subjects. The doctor had seen many people like this in the past. The doctor had seen many people like this in the recent past. Last 1 month, many people have been coming with the same symptoms. And after the prescribed medication, the patients are getting all right. So the doctor knows that this treatment works for you. So for example, if many people go to the doctor complaining about sore throat and fever, and let us say the doctor has prescribed something like Dolo, take Dolo for 5 days and it will be all right. And if that works for all the people, doctor is most likely to prescribe Dolo to the next patient as well. So predicting the disease condition, is it cold only, is it fever, or is it an underlying viral condition, or is it something else? So being able to predict such thing like that is a classification problem, which today doctors do manually, meaning we tell the conditions and the doctor will come to a conclusion that this might be the disease problem or that might be the disease problem. So this is an example of a classification problem. Then we go to the unsupervised approaches. In the unsupervised approaches, clustering is one of the common approach where given a set of observations, we want to find centroids such that we can group these observations into nearly homogeneous groups. For example, right, if there are observations like this, can I find out the colors for each of these so that the yellow is one group, the red is one group, and the blue is one group, without having the advantage of any labels. I don't know whether the red is one group, blue is one group or not, I don't really know. But even without knowing that, can I build a model to cluster and say, these are the likely groups? That's what we are trying to do. Okay, now this is clustering problem, and this is also applicable in the world of medicine. How is it applicable in the world of medicine? We will see. So all of us are aware of the COVID that happened 5 years ago, right? 2020, 2021. So during COVID, right, many governments, not only our country, but many countries, they had very few testing resources. If there is a specific test to be done, either the testing kits were not available, raw material was not available, or the testing, people were not available. There are not many medical practitioners to test also. That was also a challenge. So during COVID, right, testing resources were few, but many people had to be tested. The governments were trying to control the spread of the disease. They want to prevent the disease from spreading all around. So they had to test a lot of people. Now, because the resources are limited, but there are many people that had to be tested, the governments needed to focus on at-risk groups. They said, if you remember, or if anyone of you remember interacting with medical care or medical health practitioners during that time, depending upon what you say, they will either prescribe a test for you or they will say, no need, go home. That may be a function of your age group, your health condition, lot of other things. But based on what you say and what they understand about you or what they observe about you, sometimes they would say nothing required, go home. Sometimes they would say, okay, we will do a test for you, RT-PCR test for you, kind of. Okay, so the government needed to focus on at-risk groups. And how do they come up with these at-risk groups? These at-risk groups are derived based on the contacts, meaning I went to some place where, or somebody went to some place where there was some disease outbreak was observed. So people went to some city, there was an outbreak in the city, this guy went there and came back. Most likely this guy would have contacted. That's what is meant by contacts. Then the age group of the person, and the underlying medical conditions of the person. Based on all these, governments would test people. So subject grouping is a clustering problem. So when I say subjects, I am referring to patients, and grouping people and say if there are 1,000 people, the practitioner will say of these 1,000, say 50, say 500 complain about some symptoms, and among the 500, 100 are having some problem, and based on that 100, I will try to test or do an RT-PCR test on these 50 people based on medical conditions. So this is a grouping problem. We don't really know whether this person has disease or not, but we will try to group them and do tests on them. So this is an example of a clustering problem as applied to medical data. Then another group of other category of algorithms are anomaly detection methods. So what are anomaly detection methods? So given a set of observations, we want to find out observations that are far from others in terms of the behavior. So what is something that is very strange is what we need to figure out. But the challenge is that anomaly detection methods, the anomalies are not really very, very far away. It's not as if the anomaly lies somewhere else that you can easily spot it. Anomalies occur along with regular data, look like regular data, but are anomalies themselves. So the method for finding out anomalies is one of the methods is what is called as the nearest neighbors method. We will try to find out for each point what are the nearest points, how many nearest points are there, we will try to figure out, and based on that nearest points we will see which is an anomaly, which is not an anomaly. So this is one of the simpler methods for anomaly detection. Now how is anomaly detection applicable in the world of medicine? If you look at ECGs, right, when people do ECG measurements, you know, you go to, people go to hospital and then take an ECG, walking on a treadmill, and your heartbeat and all are observed. Then the doctor will look at the ECG printouts. There will be a printout, or there will be a printout with 7 strips or 3 strips, long strips of heart signal. Doctor will scan the signal and say you are either all right or you have a problem. So these signals are typically complex. They are typical waveforms. They are not like flat line. They are not like sinusoid line. They are not like a sawtooth. They are not like a rectangular pulse. So the heartbeat measurement is not really regular. So it is not very easy to figure out anomalies. The heartbeat pulse the heartbeat signal looks something like this. So there is a pattern like this where there is a peak, dip, and then there is some noise, again a peak and a dip, and then some noise. So there is something like that. Now within that, if there are anomalies, it is not easy to detect based on simple rules. So that is where we use anomaly detection methods, which observe the signal variation in the subject's health, and based on that they will try to identify the anomalies. So anomaly detection methods will help you understand whether a particular ECG has any anomaly or not without really worrying so much or needing to observe so much. Now up to these are basic supervised and unsupervised approaches in the world of machine learning, and then we will go to some other algorithms that we see. So for those who are in the field of medicine or even in the field of education, right, A/B testing is very common. What is A/B testing? A/B testing is to test the effect of an intervention on a population. Yes, sir. Looks like there are a lot of questions. Maybe I will try to answer them before we go back to this thing. Before we go back to the presentation. Okay. So let me go one by one. Let me go to each of these. So could you give any real-time example of unsupervised and reinforcement learning? Unsupervised learning, I just gave you the classification example, the clustering example and the anomaly detection example. Those two are examples of unsupervised learning. And reinforcement learning, one common example is trying to train a computer to play game of chess. If you know, computer defeated, say, Kasparov. Gary Kasparov was a famous chess player. In 1997, IBM Deep Blue defeated Gary Kasparov. Recently, Google's DeepMind or Google's computer defeated another player in Lee Sedol in the game of Go. So reinforcement learning today is more applicable to games because it is easy to train the computer to play the games and then give incentives. But then today there are more applications coming up for reinforcement learning even in the field of robotics. How do I train a robot to do a specific task? I want the robot to pick up the water bottle, open the cap, and then pour the water into a glass. How do I train the robot? It is an unstructured problem. I cannot tell the robot hold the bottle via command. I can only show it and then ask it to learn. So that is an example of reinforcement learning. Okay, now the follow-up question is, if it does not have any labels to learn, then at initial phases, how does the model starts learning? Yes, so the model can try to learn broad patterns. It is not as if for every observation I will be able to say whether it is good or bad. But in the world of unsupervised learning, the learning is always approximate. I will try to do something to do better, but not really, what do you call, not really be able to give pinpointed information or pinpointed outcomes for everything. Okay, then how are supervised and unsupervised learning rolled into neuromorphic computing? I am not very familiar with neuromorphic computing, but I understand that it is something to do with, say, the computing methodology that tries to mimic the neurons. One of the common examples of neuromorphic computing is deep learning, where the deep learning neurons are somewhat similar to the brain, or somewhat similar to what happens in the human brain. So there also supervised and unsupervised learning methods are applicable. You can do whatever linear regression classification you saw. You can try to train neural network models on the same tasks and then do a good job at them. So application of supervised or unsupervised learnings to neuromorphic computing, I think, is a natural extension to what you see in the traditional world. Okay, then. So the third question is, my question is how to plot the points on a straight line exactly at linear regression. So this plotting a straight line is what you learn by building a model. So when I say linear regression, right, typically you get the scatter points that are there. The scatter points will be like an Excel sheet or stored in an Excel sheet. X and Y values are stored in an Excel sheet or something, CSV file. You read the data into a Python program, and in that Python program, you try to call a linear regression model. That linear regression model will give you the slope and intercept of the line. The y is equal to a plus b or a plus bx. The a and b are learnt during the course of the training. So this straight line plotting is an outcome of linear regression. It's not as if I see the data and I throw a line at the data. No, you build a linear regression model, and then that will help you to draw the straight line. That is the answer to the third question. The fourth question is how to get loose or damaged data in machine learning. If the data quality is poor, if the data is not clear, not good, the best strategy is to throw away the data. Meaning, if I have observations about, say, 1,000 patients, but 200 patients data is unclear or of low quality or is confusing, being greedy about the 200 data points, trying to do something to impute it into the model is risky, because when you are imputing or when you are cleaning up the data, you are bringing in your own biases to the data. For example, if I am measuring health attributes of 1,000 patients, I am measuring BP, sugar, heartbeat, pulse rate, whatever, lot of things I am measuring about 1,000 customers. 1,000 patients. Among the 1,000, for 200, I do not have a good measurement of the BP. These 200 came at the end. By that time, the machine spoiled. So BP machine spoiled, or BP machine went bad, and the practitioner captured some rough numbers of the BP. It is not an exact number. Now you know that the last 200 BPs are wrong. What should I do to clean that? There are two approaches. Either I will say, I will impute all these blood pressures with some known number, the mean of the previous good values. I will take and I will impute and use it in my model. That is one approach or one school of thought. But that thought or that school of thought or process is tricky or not very robust, because by imputing the mean BP, you are bringing in your own bias. I am saying that wherever it went wrong, I will put mean value. So that's a problem that's a bias that you are bringing to the data. So a better strategy would be to clean up or throw away the data which is not useful, and try to build ML models on the data that you are confident is correct. I can build a good model on the 800, and this 200 does not really trouble me so much, because tomorrow my model has to predict on unseen data. And if I do not, if I am not able to build a good model, what will happen is the model predictions for the future will be wrong. You may say that, no, I will build my model on 1,000 observations. But when the model goes to predict on unseen data, the model is making bad predictions. That's a useless model. Rather, I would build a model on 800 and be able to predict well tomorrow. That is my answer to the fourth question, which is damaged data, lost data, unclear data, or corrupted data, or missing values. All these are the synonyms of what was the question about. Then there's another question, which is in a regression problem, if the model's predicted values are biased towards the mean of the ground truth, it tends to under predict high values and over predict low values. What steps are to be taken? Yes. So this is a symptom in the machine learning. If the model is predicting what is called a mean value only, that is a symptom of this model. What model? That's a symptom of an underfitting problem. So to prevent such things, people try to add in more features. You try to add more relevant features to the data, do feature engineering, and bring in more features that have good predictive power. So when you do that, when you bring in more features, then what will happen is the model predictability improves, and then this bias problem will go away. It will not always predict mean value. That time you will see variability. So adding more features is the remedy for bias problem, because the existing set of features are not able to get a good prediction. That is what it is. Okay. Then the next question is about difference between clustering and classification. I hope you followed the two slides. In the classification, for a given subject or for a given patient or a given customer, we make an yes or no decision. That is classification. In classification, the question will be, given this data, does this patient have a medical problem or not? That is a classification problem. Whereas clustering problem is, given 100 patients, what are their likely groups? Which is an at-risk group, which is a group that is not at risk, or which is an at-risk group, which is a group that is not at all diseased, which is a group that requires intervention later, which can take up some more time. This is clustering. So clustering is about grouping. Then the question is, clustering to set its boundary conditions is difficult to do. That is true, which is why people have various approaches for clustering. So they have something called as a elbow method, or they have something called as elbow method is an example where they will try to do various clusters and then see where this thing happens, where the bend happens, and call it a knee method or an elbow method. So that is one method, but there are other methods also. Some shadow methods are there for clustering, which will tell you what kind of clusters or how many clusters are good or bad. That is there are some thumb rules for finding out the ideal number of clusters. Then, can you differentiate between GenAI and GenAI analytics? It is like water and water bottle. Please give me water and please give me water bottle. That's a simple example. Because generative AI is like water, and you do use that for various purposes, you can say that is analytics. You will see that all of these definitions are not very rigid. I know GenAI analytics, I don't know GenAI. Or I know GenAI, but I don't know GenAI analytics. These are statements that nobody can make, because whatever you do are all related to each other. Okay. Then there is any other measurement in clustering. Yeah, elbow method is there, but there are also other methods with various measures. Maybe I'll come back to that in some way. Then, how can generative AI support multimodal data fusion in medical IoT analytics? This is what we will see somewhere later in the presentation. We are currently at the half of it where we have just dealt with machine learning. We will now go to deep learning, generative AI, and there I will answer your question as to how can GenAI support this. We will go there, sir. Okay. Then there is a question about what is the best algorithm for medical analysis. There are various algorithms, sir. There is no one size fits all. What is the best medicine to give to a patient? If I ask you that question, what can you say? For fever, it is something. For cold, it is something else. And for indigestion, it is another medicine. So similarly, based on the problem that you are trying to solve, the algorithm will differ. There is nothing like, this is the best algorithm, I will learn that it will work for everything. No. Wherever applicable, regression works well. But regression cannot work for classification problems. So you cannot do anything with regression algorithm there. Similarly, like it's like doctor saying, I only will give you Dolo. Whatever happens, I will give you Dolo. Dolo may be good for fever, but Dolo may not be good for stomach upset. Correct? So there is no one good medicine, one silver bullet are not there. Then there is a question about in the regression model, if the model's predicted values are biased towards the mean. I think it's the same question repeated. It is under prediction or under fitting model. We add more features is what we are seeing. Okay. What are the measures that are to be used for checking whether the fitted model of ours is best or not? For this, there are 3-4 things. One is, we will do what is called as prediction on the test data. Suppose I get some observations on which I am trying to build a model. I will not build the model on the entire data set. I will keep some of the data as a testing data. I will say, if I have 1000 observations, I will keep 200 observations separately and say this is test data. I will build a model on the 800 observations and then go and predict on the test data. Then the model error or the prediction error on the test data must be close to or similar to what you see on the training data. On the training data, there is an error that you observe, and the test data also you observe similar errors. Then your model is a good model. It is making similar error on the test data as it is making on the training data. That's the metric or that's the measure. But there are more, what do you call, solid measures like MAP, MSC, R2 score. All these things are there for regression. For classification, there is something called as a confusion matrix. F1 score and all. Okay, then, so please tell me a real-time example of clustering. I hope you followed the COVID thing. COVID thing was a clustering example because doctors or the government had to group people into at risk and not at risk. And in a at risk group, there can be people from different, from different age groups, but based on their, based on their health conditions, they were grouped. So the best example that I can think of in the medical world was clustering for at risk and not at risk groups during COVID. If you look at other examples today, even today, other examples can be the doctor deciding whether a particular patient or whether a group of patients will require some medicine or the other. Okay, so yeah, as per your explanation, I understood neuromorphic computing is brain-inspired mechanism with ANN. Yeah, I think that is right. Neuromorphic, most likely. See, there are terminologies that people coin. They coin more and more terminologies. But neuromorphic computing, as I understand, I also might be wrong. So please, I request you to go back, ask Google or GPT or learn from wherever you can. But as far as I understand, right, neuromorphic computing is imitating more and more brain mechanisms. It is slightly advanced than the deep learning thing that you can do. Okay. So can you suggest any wearable sensor which is to be implemented? There are many wearable sensors which are already in market, sir. If you try to design a new wearable sensor, we will be caught up with the production challenge. It's not as if we cannot monitor blood pressure with a sensor that we have in lab, but making that equipment at scale is where some companies have already perfected it. Sorry to disappoint you. But yeah, wearables like watches and all are already there. I don't know what your intent of the question was about wearable sensor to be implemented. If you are thinking about can I capture data from the wearable and build a model, that can be done. The wearable sensor will send the data to the cloud. You can, you can pull the data from the cloud and then try to build some ML models. Then, how to retrieve damaged or corrupted data in machine learning? The best way is to ignore the data. If it is corrupted, it is better to not touch it because I don't really know what was the original value. Like I just gave an example earlier, right? If the BP machine has gone wrong and gave approximate values for 20 patients or 200 patients, rather than imputing all this with a mean value, I will keep that record separately. That is how that is a better strategy because by imputing something, I'm trying to retrieve. If the original number was 1, the number got erased. Now I am replacing it with 0 or I am replacing it with 2. What will you do? Do you think that what it is correct? That we don't know. We never know what the original number was. I am imputing some other number and feeling happy. That's all I am doing. So I would request you to consider keeping aside the damaged data, working with clean data, because when you impute something into damaged data and try to build a model, the model performance will be poor on the test data, and then we will be stuck with the bad model. That is another headache to solve. And it is better to model with clean data and see what the model is performing. Okay. Now, how do we come to know that the data is corrupted? There are various ways of data corruption. Some of it can be what you can call as known methods of corruption. The data is simply missing. The value for blood pressure is 0 for everybody. Or there are patterns. The value for blood pressure is constant number for everybody. So that's how people try to figure out what is the missing data. Then, is it mandatory to find out log likelihood and log likelihood for like logistic regression? You need not do it manually, or you need not do it for yourself. Machine learning algorithms that are available in Python or R or whatever tool you use, they will do it. So log likelihood and log likelihood are already inbuilt into those algorithms. They will calculate. They will give you labels eventually. You need not worry so much about should I calculate, but yes, those are essential for classification. Then, what facial features can reduce mean and bias in regression tasks like BP prediction from images? We will see as we go to deep learning. We will see. I do not have an answer to say use this facial feature, it will work. But all that I can say is whatever images you are capturing, try to embed the images with various CNN models and then try to see which of the model does better in predicting BP. Then, neuromorphic quantum, I would request you to please hold on because that may come later, but I would request again you to go back to Google and do a basic search. Please, sorry for not being able to answer it. Quantum computing is using quantum states which are not just 0 and 1. Quantum computing essentially is a step ahead from binary computing. Binary computing means we store numbers in the computer in zeros and ones as bits and bytes, and each bit is 0 or 1. Quantum computing simply says there can be more states than 0 or 1. In a given space, instead of either having 0 or 1, I can have many more combinations, which will help us to save a lot of data. Okay, that we have advanced AI models. Why do we still use traditional ML models like STM or others? It is about the amount of energy that you want to spend for solving a problem. There is a problem that can be solved with SVM, but you want to bring in a deep learning model. It is like saying that I will bring an elephant to do a work that can be done by a horse, or that can be done by a small animal like a donkey. A donkey can pull a cart, but no, I will bring an elephant to pull the same cart. It is like that when you bring in deep learning models for problems that can be solved very well with traditional models. For the corrupted data, I think a lot of you are caught up with corrupted data. Corrupted data is corrupt. I don't know what you can do with the corrupted data. Whatever model you think is the best, you can try to apply, but that is at best an approximation. You are doing something and feeling happy about it. That's all I can tell you. And I would rather suggest that don't touch corrupted data, leave it aside, because you don't really know what to do. Then, what are the medical applications of quantum computing? Quantum computing is still in the infancy. It is not at a place where it is applicable for anybody today. People are simply trying to do something on basic quantum computing. Whatever we are doing with machine learning can go to quantum computing once it becomes very popular. All the problems will not go away. Medical problems, the tool that we are using for solving the medical problems will change. Once upon a time, it was a doctor. Now it is machine learning models. Tomorrow, it may be quantum ML models. Again, cancer-related problems. What problems are we trying to solve for cancer-related problems? Is it disease progression, or is it diagnosing the stage of the cancer? That will depend upon the model that we are going to be using. Quantum computing is secure. It is secure today, or at least people think that it is not going to break very easily. But you do not really find so much quantum computing hardware available. I don't know if maybe some other lecture or you got it from somewhere that quantum is ready to be used tomorrow. But yeah, maybe I'm not really sure about it. So brainstroke best model we will see. Reducing training time in skin cancer classification transformer, okay. How to transfer learning help, we will see. If you don't mind, we will go to the lecture. There are significant slides to cover, and I will come back from here. From where? From the quantum computing, cancer-related problems. Now, from here, I will come back. Please don't mind. Let me go back to the slides. There are many more slides to cover, or many more things to cover. Okay. So A/B testing is another algorithm where we test the effect of an intervention on the population. So what do we do in A/B testing? We divide a set of 2n samples randomly into groups of n each, such that the properties of both groups are similar. And then one group will receive medicine, one group will receive a placebo, and then we will see whether there is an effect of the outcome. By giving the medicine, did something change or not, is what we will see in A/B testing. And in the world of medicine, now A/B testing is very popular. Clinical trials are a common example. So in clinical trials, these are biomedical studies of human subjects to assess the efficacy of new treatment methods, like new drugs, interventions, and procedures, etc. And what do? We partition people into two groups, and for one group we give drug, one group we give placebo. And how do we? The evaluation of the outcome is an A/B testing problem. So I gave medicine to 100 people, I gave placebo to 100 people. The average time for the disease to go away is so much. That is what the clinical A/B testing will help us understand. Now coming to deep learning, right? Some of you have been asking neuromorphic computing, brain stroke, facial features. Deep learning is what is applicable there. So deep learning will learn hierarchical representations of the data. It's also called deep structured learning or hierarchical learning, which uses what are called as artificial neural networks. This simple mathematical construct only, not very complicated. But then we assemble many neurons together in layers, and then with that we get very high ability to predict very diverse kinds of things. So this slide is just a schematic on neural networks. Maybe for the sake of completeness, I have put it here. A single neuron is what you see on the top left. It will take in inputs, apply some weights, do a weighted sum of the inputs, W1j into x1 plus W2j into x2, and so on. So weighted sum of the inputs are taken, an activation function is applied on them, and an activation value is obtained. All this happens inside one neuron. Typical activation functions are sigmoid or ReLU, and whatever is this image that you see on the top is one circle here. Okay, this neuron takes in inputs from these three, does a weighted sum, calculates an activation, and sends it to the two neurons to which it is connected later. And this is precisely how brain functions, which is why they call it a neural network. And in the neural networks, there are simple neural networks, there are deep learning neural networks, and so on. So these are various kinds of neural networks that are available. Now, these neural networks also have two other architectures. So one is called as a convolutional neural network, and the other one is a recurrent neural network. So convolutional neural networks are CNNs. They work on images and videos. They generate spatial understanding. And finally, the context, meaning if you give an image, like the question that was asked now, if I give an image, If the BP of a person is showing up on the face of the person, then CNN, by looking at the image, can generate numerical features which will help us in predicting the BP. It will not give us a BP number directly, but it will give us a vector of numerical values from the image with which we can go and then build a model to estimate the BP or the blood pressure. Similarly, RNNs will work on text. Recurrent neural networks are the NLP world. They work on text and they generate temporal understanding, meaning a person is saying something, RNNs will help you understand what the person is saying. The words come one after the other. You understand things in time. I am not feeling very well. I am feeling hungry, or I have a headache. All that words are told one after the other. Those words are understood to generate an understanding. That is what RNNs will do. So some examples of visual perception are this. We try to classify, we try to do object detection, we try to do instance segmentation. So these are common examples of visual perception. And coming to the world of medicine, what do we do with all these CNNs is what we are going to see. One of the very popular applications of deep learning for computer vision or CNNs was about chest x-rays. So there are diagnostic tests like chest x-rays and CT scans. These generate images of the lungs of the person. So a person is not feeling well, they go for an x-ray generates an image. Typically, a radiologist will look at the image and say whether there is a disease or no disease. That's the common thing. A radiologist or somebody will say, okay, looks like there is a problem or looks like there is no problem. And they are calling out their, their classifications from training. But here, based on historical data that is available, we can try to train an image classification model or an object detection model to say whether a particular X-ray, the lungs are normal or diseased. If the lungs have a disease, the model will classify it into a diseased lung and will be able to tell us that, okay, there is some problem with this image, and also be able to identify the regions where the problems are. So you can think of it like a classification problem to say diseased or not. You can also consider this to be a detection problem, object detection problem, because I am able to identify or outline the regions where there are problems. Okay, this is an application of deep learning for vision, and predicting the blood pressure from facial features also comes into the same category. I take facial features of people and measure the blood pressure. I will try to use a convolutional neural network on the images to generate 1D vector of features, and that 1D vector of features I will try to regress, or I will try to predict the blood pressure based on these input features. So instead of taking selected features like computer vision, in the traditional world of computer vision, there used to be something called as feature selection. Instead of that, if you use convolutional neural networks, they generate a 1D vector of image, and that 1D vector of numbers can be used for predicting various things. Then natural language processing is understanding text and seeing what people are saying. Simplest example is sentiment analysis. The comment is good or bad. Then chatbots came, then Alexa came, and then finally a robot called Sophia came, which would answer people in natural language. It would also have emotions, talk to people and all. So what is an application of natural language processing? One application of natural language processing is monitoring clinical trials. So whenever doctors are talking to patients, these recordings can be used to see whether the patient is actually healthy or not. This is more applicable in the world of mental health. So this is a practical problem that we solved, and I'll share the presentation with all of you anyway. The link is below. But this application was about when there are clinical trials of mental health drugs. Doctors will interview volunteers who are being treated and rate the progress of treatment. This interview is a voice recording. Doctors will ask something, patients will say something. It's a voice recording, and then we can build an NLP solution, process the video, process the audio, convert it to text via transcription, and the transcribed text, on the transcribed text we can try to extract various things and then rate whether the interview was very well or not, whether the patient is doing well or not. All this is possible with the world of natural language processing. Then moving quickly to generative AI. This is the crux of the presentation that I wanted to cover anyway, so we'll come here. So generative AI, what is the differentiating feature between regular AI and generative AI? Whatever you have spoken so far is regular AI. So in regular AI, there are many inputs. In the price of a house example, we give many inputs and then you predict the price of a house. In the image classification task, we give pixels, or we give an image which contains many more pixels, and we get a single class of whether it is cat or dog. So there are many inputs to the model, fewer output from the model. This is the characteristic of regular AI. But the moment you go to generative AI, what you see is the inputs are few and the outputs are many. For example, on the left side, you go to an image generating model and say astronaut riding a horse, then what you will see is an image like this generated. I asked 3 words or 4 words, I got a rich image. There is an astronaut riding a horse. Similarly, I go to a text generation model and say twinkle twinkle, then it generates this text saying twinkle twinkle little star, how I wonder what you are. So by giving 2 words, I'm able to generate many words. So this is the fundamental difference between regular AI and generative AI. Generative AI can generate more numbers or more outputs based on a fewer inputs, based on the model learning, based on the understanding that it has. So there are fundamentally 2 classes of generative AI. One class of generative AI is for vision. So GANs, VAEs and art diffusion models. These are the class of generative AI methods which are applicable for vision. Another class of generative AI models are for language or text. And this is where you would be hearing about, or this is where the popular GPT, chat GPT, large language models, all of them fall into these slides. So large language models is a transformer based architecture. They achieve nearly general purpose understanding and generation. They are trained on a huge corpus of text that is available on the internet, but they have millions and billions of parameters. They require significant compute resources for training. Somebody was asking, can I do transformers? Yes. If you have a very good GPU, you do not care about the training cost, then transformers are something that you can do. But if you are limited by your training cost, I would request you to consider simpler models, because all of us can only do as much as the hardware is available to us. So these transformer models or large language models use self-supervised and semi-supervised approaches for training. This is what they do. Then what are the generative AI applications for medicine? The generic abilities of generative AI are the following. So for traditional machine learning tasks, like say classification, clustering, regression and all, GenAI models have better abilities than simpler models, just because they are more complex or they have more parameters. Okay, if a horse can pull a cart, an elephant can definitely pull the cart. That is how I would frame the first statement. Because generative AI models are more powerful, they will do a better job than regressional classification at the regular tasks. So on tabular data, generative AI models can do data cleaning, regression and classification. LLMs can be used for text classification or summarization. LLMs can also be used for named entity recognition and information extraction. If the doctor is writing a medical report, what is the patient name, what is the disease condition, what is the, age of the patient, I can very easily extract if I'm using an LLM than using the previous NLP methods. So they are very commonly used for extracting structured data from unstructured text. There is a medical summary report. I want to extract a few parameters: patient name, treatment duration, medical condition, what is the medicine prescribed, when is the next visit. If I just want to extract a table out of a medical report, that can be done using LLM applications. So they can, more importantly, right, they can be used to create high dimensional representation of input data for clustering and anomaly detection. If I want to do anomaly detection or clustering, generative AI models can do very rich representation compared to what the traditional deep learning or the machine learning models can generate. Now coming to our final application of medical IoT data, right? Almost all data generated by IoT devices, whether it is watches, whether it is say ICU room equipment and so on, all this data is more or less structured data. It is not unstructured data, because a watch will not generate a report in free-flowing text. A watch will only send vitals, like this is the blood pressure, this is what is happening and so on. So these data is typically about vitals, which is BP, heart rate, temperature, respiratory rate, oxygen concentration and so on. Sometimes it is physiological data as well, which glucose, cholesterol, body weight. It is about activity data, how many steps did the person walk, what is the sleep quality, what is the exercise level. It can be about device operational data, environmental data, medical adherence data and so on, and eventually medical imaging and diagnostic data. So only the imaging data is unstructured, but most of the other, and maybe the doctor reports themselves are unstructured, but most of the other data is always structured, more or less structured, because it's all numerical data that can be captured. So for AI ML, or for the world of AI, what are the use cases in medical IoT data? Remote health monitoring is one example where you can use AI ML using anomaly detection and so on. Early warning systems are another application where we can use early anomaly detection models on cardiac things and so on. And then diagnostic support on X-rays, ECGs, etc. This is what we saw in the X-ray classification. We can use deep learning models that will run on these X-rays or ECG data and identify whether a person has a specific condition or a problem or not. So this is a generic set of statements that are applicable for AI in healthcare when you use IoT data. But then coming to generative AI, you saw that generative AI can do more. So what is the more that generative AI can do? Generative AI can do enhanced medical imaging. It can do real-time contextual decision support. We will see what each of these is as we keep going. No, we will see. Please give me 2-3 minutes to cover this. And it can provide help in telemedicine chatbots. It can provide automated documentation, note generation, multimodal data fusion and summarization it can do. And it can eventually synthetic data generation is also something it can, achieve. So what is each of this we will see. Okay. So what is enhanced medical imaging? If you are familiar with MRI scans and PET scans and so on, right? Typically doctors, when they prescribe scans, there can be these scans can be done at different resolutions, meaning one of it can be low resolution scan, which can be faster, and then they require lower dosage of harmful radiation, and the scan is done quickly, but the resolution is low. Whereas if there are very specific conditions that the doctor want to measure, the doctor may prescribe a high clarity scan. Okay, so if you do a low resolution scan and go, the lack of clarity may hinder proper diagnosis, and then the doctor may say, no, I want to do a high resolution scan. Okay, so today generative AI models, there is a company called Subtle Medical which is already doing it. So today generative AI models can enhance low resolution scans to high resolution. I take a low resolution scan, make it better, and when I am making it better, I am not losing the ground truth. My reconstruction is very realistic or very faithful, so that the doctor can take this at face value without any problem. So the point is the requirement for high resolution slow tests which are more harmful to the patient are gone. With low resolution tests, we can upscale the image, do the diagnosis. If the doctor still has a problem after upscaling, the doctor says, okay, this looks somewhat okay, but still have some suspicion. On that suspicious thing, I want to do some analysis. Then the high resolution scan can always be done. After all, nothing will substitute the ground truth. So a high resolution scan is the ground truth. The point is, by using generative AI models, the need for generating the ground truth or high resolution images for many people who do not require it will be gone. So it will save time, it will save resources, and prevent unwanted exposure to radiation for patients who are not really at risk. So this is one of the applications of generative AI in medical data. A second one is about contextual decision support. What is contextual decision support? Based on medical knowledge, generative AI can generate explanations for particular observation. It can synthesize large volumes of unstructured data and fetch relevant reasons. For example, right, there can be a patient who will say, I took Dolo, but my fever did not subside within 2 hours. Then the context can be that this patient took Dolo, but he still took an ice cream, ate an ice cream, and that is hindering the fever from going down. So generative AI can parse through or read through large volumes of text, or would have read through large volumes of text to ask relevant questions. And based on that, it will help you understand. When you say this is some condition that I am observing, it can ask you some more questions, and it will be able to provide rare conditions that may not be accounted for by most doctors. And some of you might have heard that ChatGPT was able to diagnose some diseases which are not really predicted by doctors. So while doing this, it will account for the personal history of the patient, and it will help in providing a real-time support to the patient. So this is another example of generative AI in the world of medical support. Then the third application is chatbots, where chatbots can help answer questions based on medical knowledge and also the user provided context. Users today can upload their medical test report and ask questions of the chatbot, and the chatbot will understand what is being said in the report and then try to answer faithfully. And it can also generate reports in required formats. This is another application of generative AI. The fourth application is automated documentation. So whenever doctor is doing diagnosis, doctors tend to speak, and typically in the olden days, people used to take notes, or later people used to record. Whenever doctor was saying something, by looking at what is happening in the patient, or whenever they are doing a surgery, or whenever they are doing some test, the recordings used to be voice recordings, and that was to be transcribed by humans. So medical transcription or medical coding is what you would call. Medical transcription was the world where audio recordings had to be converted to written text. That was a very popular, what you call, problem 10 years ago. But today, all that is being done by generative AI. You speak and generative AI can do the transcription, which is what you get as live captions in what do you call audio and video calls. Today, like in a team meeting or Google meeting, right? You can enable live captions, and as I speak, it will show up the captions. So it is enabling reduction in manual effort. for healthcare practitioners. Then one of the other applications is multi-modal data fusion. So when we say multi-modal data fusion, by that we mean the LLMs being able to combine data from various modalities, from images, from text, from sound, and so on. For example, right, for the heartbeat, there can be a scan of the heart, there can be a sound that is generated from a stethoscope or some other what you call device, and there can be text that is generated from the doctor's prescriptions. All that it can understand, it can summarize and then generate reports. Okay, so this is a very unique thing that the generative AI can do. This multi-modal fusion is not possible by the other traditional methods until now, right? Some of the things that GenAI can do, ML also can do. Some of the things that GenAI can do, deep learning also can do. But fusing multiple modalities and generating reports and so on is something that is, like you can say, is unique to generative AI models, and is not really possible by other methods. Unless you put large effort, you cannot solve multimodal data fusion using, say, simple deep learning. Then some of the other applications are synthetic data generation, where the image generation models, GANs and VAEs, they can understand patterns in visual data and create variations that are similar to the actual data. What is the use of the variations? These variations are variations of the original data that is observed, and they can be used to train people. For example, right, if you have, say, 100 chest X-rays and you are training a radiologist to classify these X-rays or whether they are problematic or not, then if you want to provide more and tougher challenges, you can generate more and more radiological scans or more and more radiological images, and then see whether a radiologist is able to classify them or not. So one of the most common applications of synthetic data generation is to enhance the training for traditional models. Then one of the last applications is to do simulation and training. Today there is a NVIDIA solution called MONAI, M-O-N-A-I, where it can generate near real training imagery. It looks as realistic as you are seeing it in person, and it is similar to a digital twin which has enhanced visualization simulation ability. For example, with the NVIDIA tools, you can go to sections of the human brain. You can apply a section somewhere, cut and see what would happen. And it is very commonly used in training and learning for people. And there is also an ability to introduce variability. Some patient has a high, say, medical condition. Can you show me how the organ of the patient will look like with that medical condition? Then this MONAI can generate near realistic images for that thing as well. So with this, I come to the end of the presentation. Maybe I'll come back to the questions and answer. But I hope that some of the questions that you have been asking are answered. And maybe let me see if there are more questions. Coming back, yes. So for the corrupted data, please ignore the corrupted data. Medical applications of quantum computing, any regular ML problem you can solve with quantum computing, but again it is about the matter of resources. You can use low resources and solve the problem, or you can use lot of resources to solve the problem. That is a choice that we will have to make. For cancer related problems, if it is about images, deep learning models are the one. If it is numerical data, then there can be, say, other models. But it depends upon what are you trying to do for the cancer related problems. Quantum computing is secure, at least so far it is secure. And what is the best model for brain stroke? It is the model that you are going to prescribe for brain stroke is dependent on the kind of data that you are measuring. If you have visual data, it will be something else. If you have numerical data, it will be anomaly detection models, or it can be classification models. If I have some numerical data measured and I will try to say what is the probability of a brain stroke within the next 1 day, within the next 1 week, it can be traditional machine learning models. But if you are dealing with images, it can be deep learning models. Okay. So to reduce training time in skin cancer classification, when we use transformer, okay. So when you use transformer, I think you are using vision transformers. VITs are what they are called, because skin cancer is an image problem. There are images of skin cancer, and that skin cancer images, people are trying to classify whether the image is good, whether the image has cancer or not. Vision transformers are known to be bulky, sir. Typical CNN model will do well there, but if you are using vision transformers, the training will take more time, because transformers are more bulky or more complex than the simple CNN models. Okay, yes. How does transfer learning help when training deep learning models on limited COVID-19 medical training data set? So transfer learning is like taking a trained person. I want to recruit somebody in my hospital. Do I recruit a fresh graduate, or do I recruit somebody with experience? Transfer learning is like that. A person with experience knows a lot of things by nature, by default. Similarly, transfer learning will help you to speed up. So if you are trying to build a better model, you can try to take transfer learning and build on the model and then go on. That's what you can do. Then Can't we use the finding missing value techniques, which we use in dealing with CRD, RBD, and LSD? We can use, sir, but whether the model is good or not is something that you will figure out later. So the simple test for all of us who are trying to solve the problem of missing data would be the following, which is, I have some data set, there are some missing values, fine. You create two data sets. One is a test data set without any missing values. The test data set is completely clean. It does not have any missing values. It is 20% of the overall data that you create and keep separately. On the training data, you do two groups. One is training data without missing value imputation. One is training data with missing value imputation. So you have two sets of data, which is very clean training data, imputed training data. And you build models on each of them. Same model. If you are building regression model, build regression model. If you are building SVM or classifier, you build the same model on both of them. Same architecture. If I am using random forest with say tree depth of 10, use the same random forest with tree depth of 10 on both. So you will get two models. One is a model trained on clean data. The other is a model trained on the corrupted or the imputed data. Now use these models to score on your test data. You have kept your test data separately, no? So please go and evaluate on the test data. Whichever model gives you good answer, you take it and go. I have no other things to say. If the model with imputed does well, then that's fine for you. If the model that is not imputed does well, then you have your answer that imputation may not always help you to get the correct answer. Okay, then what are the probable latest research articles in this area? So today GPT, Perplexity Pro, Gemini, all these will give you, sir. It's not as if there is one single source of truth. I'm not the sole arbiter to tell you that this is the latest research. You go and ask Perplexity Pro if you're a retail guy, or you go and ask Gemini or GPT, you know, they're able to come up with latest research. Then nowadays accuracy is very important, especially for applications like medical prediction. Correct. AI models generally provide better accuracy compared to traditional models. Correct. Should we consider AI? Yes. If you are able to afford reasonably good hardware for training, then I will always go to a better model. If the hardware is limited, then I will choose a model that works best given the limited hardware. That's all. I want to go fast. Fine. If all that I have is a cycle, I will use the cycle instead of running. If I have a motorcycle, then I will switch to the motorcycle and ditch the cycle, because motorcycle can go faster. The motorcycle or a car or the cycle are all examples of the hardware that you have. Then an appropriate simulation platform for doing analysis, specifically for beginners. What is a simulation platform? I do not really follow. Maybe if Dr. Hemalata is a medical doctor, then maybe I'm sorry, madam, I'm not really aware of a medical simulation platform that can help you to do analysis. In the machine learning world, Python is one that all of us commonly use. But if your question is more about the medical simulation platform, I'm very sorry that I do not have a ready-made answer. I'm not really aware of what is a good platform to use. Then, can you explain the use of different layers in the CNN, convolution, pooling and all? Yes, we can understand there is a good course, CS221N. There is a Stanford course on convolutional neural networks. That is a good start for all of us, CS231N or so. You can use that model, you can use that, what do you call? You can go to that course and then try to understand what is there in that course and see. But for most of the people who are going to be practitioners, you need not really worry about what is the layer does. So understanding, while the understanding is essential and very good, it may not be essential for most people who are using it. I pasted the link in the chat window. Maybe you can actually go to the that course and see. So CS231N.stanford.edu, that will explain what each of these layers are. Okay, I think that was here. Explain the use of different layers. Can you please explain more details about CNN in medical? Yes, please go through that CNN course at high level. I know that if you are doctors, you need not understand everything in detail. But if you are engineers who are trying to practice, that course will give you a good identification. So which model is good for speech articulation defects? Again, these models you have to try and figure out, Renuka madam, because people try out various models and see. There is nothing like one model fits all. Part of the work or part of the research is about trying out different appropriate models and seeing them that which of them are good. Okay. Some platforms where we can get free API for generative AIs and build models. Building models and all is not possible, but Grok, Grok is a platform that will provide you some free LLM calls up to some limit. It is not available for eternity. You cannot do as many calls as you want. But GROQ, Grok is a platform where you can register with your personal email ID, get an API key, and with that API key, you can make calls to LLM models. That is one. Then, in the regression problem using face images, for example, predicting blood pressure, if the model's predictions are biased towards mean of the ground truth, what is the additional features? It can mean two things. It can either mean that the facial images has no indicator of blood pressure. The person might look very calm and the person might have high BP. Okay. So if the model is only predicting mean value, one of the reasons is that there is no predictive power in the facial image. You take image and say it is related to blood pressure, it is related to heart rate. That may not be true. That is one possibility. Another possibility is that if you are asking what additional features do I add, typically if I'm using facial features, I will use convolutional neural networks. I will try to pass the facial features through a CNN, like faster RCNN or ResNet, and use that CNN features to predict the BP. That is what I will do, rather than using half transforms and all. Then, which processor architecture is best suited for LLM implementation? If you are referring to implementing an LLM on your own, these are all NVIDIA GPUs. But if you are referring to using the LLM model, today most of this is on the cloud. Nobody is really if you are going to for inference, right? Most of the people are on the cloud. No, not many people are buying hardware for that. Then Raviranjan sir has a more light-hearted comment. I need another GPT for understanding short words. Maybe I need to update more. Yes, sir, that is true, because there is always a trade-off between how much to cover and what is the depth. We can talk about linear regression itself for 1.5 hours, but that may not be the objective, right? Then, are there AI websites for NLP processing? You can go to Grok, GROQ. That is something that you can use. To find efficient schemes of data security in IoT, which will be good to carry on research with generative AI or quantum computing. Currently, generative AI is what is available. Quantum computing will become more popular in the future. This is what it is, and I think Raviranjan sir likes my straightforward answers. Thank you, sir. What are the ethical issues of GANs in deepfakes and data privacy? The deepfakes and data privacy with GANs is not a significant challenge, because you can say that deepfakes are bad, agree. But then the images generated by GANs can also be used by training. So it's like a knife. I can use the knife to cut a rope that is tying a person. I can use the knife to cut apples. I can use the knife to cut useful things. I can also use a knife to harm somebody. So technology is always dual-edged. It is not very appropriate for us to think of, should we ban the technology because it is bad? That is not a question, because then we will end up banning electricity, we will end up banning internet, we will end up banning knife itself. So that will not really be working. Then, explainable AI classification based on EEG signals can be done. Yes, there are explainable AI methods like SHAP, 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 and LIME, and Deep SHAP. These are some names that I request you to go and read further. SHAP, LIME, and the Deep SHAP. This can provide you some guidance on how to explain medical imaging methods. Then, yeah, explainable AI is there. We did not cover it because, yeah, again, short time and many things to cover, right? So please try to read up on GANs, SHAP values, and so on. Then, explainable AI classification based on ECG signals can be done. Yes, there are tutorials available. I would request you to please go and read up or find something on the internet. This would require some familiarity with Python. You are comfortable coding in Python. You are familiar loading data from multiple sources in Python. Then I think this EEG signal training and all can be done. Not a problem. Then, GAN models are used only with images, or any other modality also can be implemented. The generative adversarial networks are primarily trained for images. They can work on, say, text data, numerical data also, but they are actually trained for images. Their power comes into play when you generate images. Otherwise, you can generate anything else also with that. Then, how do we balance GenAI's potential for improving healthcare with the need for security and explainability? This will come. The security and explainability parts will come later. For example, if you look at various technologies, for example, again, if you take cars, automobiles, when they just came in, they had very low mileage, they had very high pollution, they were very dangerous and so on. As people saw the problems with the device, they would improve. Airplanes also had problems originally, 1940s, 1950s. Airplanes had a lot of problems, there would be crashes, people would suffer, but today airplanes are reasonably safe. So the development of security, development of explainability will go along with the development of adoption. Without adopting, nobody will work on the security. Nobody is using it. Why do you need to care? is what a security professional will say. If there nobody is using it, what is the need to explain? Is what an explainability guy will say. As adoption grows forward, that is when these things also will pick up. Then, for thyroid cancer detection classification, which model can I use? If these are images, thyroid images of the thyroid gland and all, you can use deep learning models, CNNs, convolutional neural networks, are what we can use for thyroid treatment or for thyroid cancer detection and classification. Then GenAI models for prediction for medical. In our PPT, GenAI leads less inputs, give us more outputs. Yes. What GenAI models are available is what you can use, but it is more apt to the problem that you are solving. If you are generating images, you will have to go to GANs. If you are generating text, it will be something else. Okay. For a beginner for research in medical cancer classification, how to start research work? Today, that the world of research has gone one step further compared to Google. Earlier, we would go and ask Google to say what is the latest research. It will give us some papers. Some of the papers may be behind paywalls. Some of the papers will be an archive. But today, you go to any LLM, Perplexity Pro kind of thing, and ask what is the latest research in this area. It will give you, and it will give you in words that are applicable or that are useful for beginners. So that is not a problem at all. So you can try to do that. Then synthetic data generation is same as data augmentation. Correct. Synthetic data generation is same as data augmentation. But again, if you have 100 observations original data and you are augmenting with 1000 observations synthetic data, you are flooding the original data with synthetic data. But when we are saying synthetic data generation in the context of images, in that context, the model has learned thousands of images, which is why it is able to generate a realistically looking image. That is the context for synthetic data generation in the world of what do you call generative AI. I think that is the end of the questions, and thank you. Praveen sir, any other thoughts or questions for me? Okay, if there are no other questions, right? Thank you very much for the opportunity, and thank you participants for listening patiently. Okay, something has come more. Which model for ECG signal classification? ECG signal classification is a time series data kind of a thing. It's data in time. You can use time series data, time series models as a beginner level, or you can use anomaly detection models. Don't try to treat the ECG problem as an image problem. You treat it as an image problem. That is an overkill. I look at ECG image and try to do something is an overkill. Try to take the ECG values as a numerical features, and you can build models using RNNs, LSTMs, transformers, all those you can do. And then with that, you can try to build anything. Then synthetic data generation used for text data to yes. Synthetic data generation is used for text reporting generation. Doctor says some notes. Synthetic data generation is useful there. Yes, that is true. Yes. Any other questions, participants? Praveen sir, if there are any other comments now, please place them here. Okay. If there are no other questions, then again, thank you all for the patient participation and questions, and thank you, NIT Puducherry, for the opportunity. Praveen sir, can you hear me? You are there?
Sir, can I audible, sir?
Yes, sir. I can hear you now.
Yes, Professor. Thank you for the wonderful session. You could see like participants are so active and they are posting a lot of questions. It shows how much your session is interesting and how they are involved. Thank you so much for the informative session, Professor. Thank you for your valuable time. And in future, we can
Thank you, sir.
try to
Sure,
have
sir.
another workshop on session. Thank you.
Yeah, definitely, sir. I'll share the PPT. You can share it with the participants, sir. Thank you very much.
Yes, Professor. Thank you.
Yeah, thank you all. See you.